lecture. That doesn't seem to be the case. Then let's continue with the content. We discussed and introduced the ensemble, which is the set or pool of A identical systems. And each of these systems can have a certain number of degrees of freedom. And that's related to the number of atoms in the system in terms of 3n in total for n atoms. And then you still have 3 translational degrees of freedom. And in terms of rotation, you'd have to subtract 3 for 3D objects, 2 for linear objects, and 0 for spherical objects. Okay. The ensemble has capital A systems, each with that number of degrees of freedom, and it's thermally equilibrated. And we discussed which would solve Schrödinger's equation for that system, right? One out of the multiple states that you have in there. Now, it's fairly abstract. We are not even mentioning which Schrödinger equation you're looking at here, right? So it's the atomic, the nuclear motion Schrödinger equation, the Schrödinger equation for the electrons, the Schrödinger equation of some other degree of freedom, let's say a photon interacting with your system. We didn't specify that, right? And we then asked this question about the distribution of states in the ensemble and introduced for that purpose the number of systems in a given state J, right? So all those systems among the A systems that happen to be in state J, you sum them up, and that number is AJ, capital AJ, a small case letter AJ. And then, of course, you can easily make a figure like this where you have the state, right? So typically in the following the energetical ordering, the state number of state here. So you can imagine a ground state and then excited state and so on. And the number of systems in the lowest state in equilibrium, right? You'd expect that number to be the largest. And then the next higher lying state should be the next largest, and so on and so forth. Now, since AJ is the number of systems in a state, AJ cannot be negative. Its smallest value can be 0. And as you add up all your AJs, you should recover the capital A. Now, Ludwig Boltzmann showed us how to derive an expression for AJ using some very basic math arguments. And we were stuck in that when we stopped on Tuesday. In particular, he proposed to use the ratio of these occupation numbers of 2 different states, right? So literally the ratio, let's say, between this state and that state, and he's asking about this ratio. It should have to do with the relative energies, right? If one of the states has a much, much higher energy, that ratio should change, right? So That means in terms of a relative energy, this should be some function of the energy difference, K and J. Now, similarly, of course, we can consider any other state L and write the ratio between AJ and AL. And that ratio should also be then the energy, the function of the energy of EL minus EJ. So nothing new here, but then we do something which is quite common, trick from the toolbox when handling equations. We like to add a zero. Okay, it's like in sums and subtractions, we like to add zeros, and divisions and ratios, we like to multiply with one. So let's do that. Let's add a zero here. And we write EL minus EK plus EK minus EJ. Okay, so we've added a zero. Okay, now let's call this, just to make this super crystal clear and not to get confused with all these indices, let's call this X and this Y, okay? So then we have F is a function of X and Y, okay? Now, as you add that zero there, you can also multiply with one the other side, which is AJ divided by AK, AK divided by AL. So now to go from here to here, we added a zero. And to go from here to here, we multiplied with one. Okay. Now, you see you have this product here, right, which must be the sum. So that means you have an fx times an fy, right? So this was your AJ over AK. This is your AK over AL, right? So in other words, what you have here is that this funny function, which we don't know, right? This function, we'd like to know this guy, right? We'd like to know f, right? This function must observe this fact that if you multiply it with different arguments, it should be the same as the function for the sum of the two arguments. Now, which function in your experience does that? Any idea? Hands up. In the back, yeah. Completely right. Yes, the exponential function does this, right? So f could be, right? It's one function that does it. Maybe there are others. we don't care, but that's certainly not wrong. Okay. Okay, so that means then this is Boltzmann's ansatz for F. Okay. Now, if you follow that reasoning, you can go backward and it all makes sense, right? And that's often part of the discovery that something really simple, you just try it, and then afterwards you check if it's true, right? That's an ansatz. Often when you look at differential equations, you also should have seen this, that you guess some ansatz, right? So that's what we are doing here. We don't do a statement that this is the one and only function that does this. So then we go back and we say, well, so a j over a k. Now we know our function, this ratio, should be something exponential in the energy of k minus the energy of j. Okay. And we are practical people. The probability that this exponent is just exactly this difference would be weird, right? Weird coincidence. So let's plug a factor in front of it and let's call it beta. Now, we'll discuss beta later on, but it will turn out it's key. But for now, let's just call it beta. And let's keep on operating on this object, because now, of course, we are tempted to multiply this, to solve this for aj, because aj is this occupation number I started out with, right? And I promise you, Boltzmann can tell us something about it. So Boltzmann tells us aj must be ak multiplied with this exponential function with beta ek. And now I make use of the fact that the exponential function is separable, and I factor out my beta with ej. Okay. Now, what you see instantly here is that this prefactor here is not a function of j, which means I can pick whatever k I wish, right? Or in other words, as I play with different j's, right? If I go from j, from my index j to p, q, r, s, and so on, I can keep my k fixed, right? So it's the same constant, right? It's a constant, okay? Okay, so we like to call constants c. So aj is some constant times e to the minus beta ej. Okay, very nice. Now, this is how far we can get with this simple consideration. But now we can make use of something we also stated in combination or in the context of the ensemble, namely, we can try to eliminate the C using further knowledge. In particular, what do we know? We know that as we sum over, so that is the sum over our AJs, must be capital A, right? So if the sum over capital AJ equals A, and we have an expression for our AJ, we can simply insert it. So A equals sum over AJ equals sum over C times e to the minus beta EJ. You see is a constant independent of J. So it's C times the sum over e to the minus beta EJ. Now, when you sum over something, that something is being averaged out. Right? It's as if you integrate over a variable. It's gone afterwards. So that's a big J independent constant. And this constant we call Q. And Q the sum over all states J of e to the minus beta EJ is known as the partition function. Yeah. In German Zustandssumme. Which translated means sum over all states, the sum over states, okay? And it is one of the key properties in statistical mechanics. A lot of this course will deal with the question, how can we express macroscopic thermodynamic observables in terms of Q? Now, just to remind you, the EJs, the energies of the states, are just eigenvalues from your Schrödinger equation of one system in the entire ensemble. Okay? So through simple operations and this ensemble concept, we eliminated Avogadro's number. Okay? So it's very impressive. All right, so now we have this Q. That means our A equals C times Q. And this, of course, means C is simply A divided by Q. Let's insert that. And our occupation number, which was C times e to the minus beta EJ, becomes A over Q times e to the minus beta EJ. Okay? It makes sense that the occupation number would grow with the size of your ensemble, right? But that's, of course, something we don't like, right? So if your ensemble of system is supposed to be mimicking some real life sample, macroscopic sample, you wouldn't like your numbers to depend on the actual size of it. You want to operate per unit, right? We want to normalize things. And then afterwards, you scale with the actual size of your system. So that means this AJ is not yet normalized by sample size which should correspond to which is being mimicked by your ensemble, right? The ensemble with these non-interacting systems is sort of a proxy for the actual sample size. The macroscopic, right? We said that this capital A is very large, right? So Avogadro kind of numbers, right? Okay, but that's easy for us. All we have to do is normalize. So divide by the size, right? Divide by capital A, right? So what we should really be looking at is AJ over A. Right? Okay, so AJ over A is the number of systems in one state over all the possible number of systems, right? In other words, that's a probability. That's the probability Bj, probability to be in state J. Probability for any given system in your ensembles to be in state J. And this probability, if you want to calculate it, you take your AJ, right? So this thing here, and you divide it by A. So Bj equals e to the minus beta Ej divided by Q. Now, you could, or maybe should, question me and say, well, is this really a probability or just because you say so? And we can do a simple test. A probability must obey must sum up to 1. Right? So let's check this. So sum over Bj equals 1. That's the question mark. Let's plug it in. Sum over Aj over A equals 1 over A sum over Aj. Okay. Now, what is the sum over Aj? It's A. So the whole thing is 1 indeed. Now, this is the Boltzmann probability. Also known as Boltzmann probability. And e to the minus beta Ej is also known as the Boltzmann factor. Okay. And Q is the partition function. So the Boltzmann probability is the Boltzmann factor divided by the partition function. Now, a brief remark on this beta. Oh no, what did I do? Does anybody maybe know already what beta is referring to? Yes, please. The gas constant? The gas constant, no. It's not entirely unrelated, but it's not. Yes, please. That's correct. It's also known as the inverse temperature, right? Beta equals 1 over kT. T is the temperature, and K is a constant. And the B, it's KB, is supposed to remind us of Boltzmann. So it's Boltzmann's constant. And the exponent in total has to be unitless. Right? So the units of Boltzmann constant must be energy over Kelvin, right? Or energy over temperature. Right? So specific numbers are 1.38 times 10 to the minus 23 joules per Kelvin. So that takes care of the units which we have. And we can now ask this question. As we look at the probability, your Boltzmann probability, let's say of one state, right, Pj, it must be between 1 and 0, obviously, right? And that probability will go down as your energy goes up, right? Ej, right? So as your state, as your state's energy goes up, the probability of occupying that state will go down. And suppose your energy is 0, so your probability for the lowest state would be the largest. I don't know what's happening here. So you have an exponential function, right? Now that happens at 1 beta, right? Now you increase your temperature, and what happens to this Boltzmann probability, right? You're increasing the width of the exponential function, right? So for a higher temperature, you should see this. So with increasing temperature, the probability to occupy higher lying states increases. I'm sorry here. So this is now the spectrum here on the x-axis. That's sort of plotted as a continuum. And so this shouldn't be the probability of just one state. So if I tracked only this one state, right, J, then that will be Pj, but now this is the probability for any state. Yeah, so as T grows, the probability grows, right? The higher lying states will become more likely to be occupied. So in the 0 Kelvin limit, only the lowest state. So at very low temperature, you would see a very sharp exponential decay, right? Small t. large T. Now, this is something you probably know already from your lab experience. But now you see it derived based on very few assumptions, right? And not complicated math, right? This is, I hope you can agree with me. Are there any questions on this? All good? Okay, then yes, please. No, you're right. This shouldn't be EJ. It should be just any E. So J would be just one level here, right? This could be J, this could be K. So let's call it En. Okay, so with this, I'd like to come to the third chapter in this course, which is about states. And we will now look in this chapter at a whole bunch of functions or properties you're familiar with, and we will try to express them in terms of Q, partition function. So at least in principle, if you solve Schrödinger's equation for enough solutions, you can calculate Q, and you have expressed your macroscopic variable in terms of Schrödinger's equation on the solution cell. So let's begin by the energy. Before I enter the energy, a little question. Why do we obsess so much about the energy? What's so special about the energy? Why not some other property?
It's because minimizing it tells us what state the system is in.
That's right. Right. It will determine which state we have, right? Aggregation state. Right? Are you liquid, solid, or if solid, which crystal structure, and so on. Right? Incredibly important. Now, in quantum mechanics, the energy is the expectation value of the Hamiltonian operator. And that Hamiltonian operator in your first postulate of quantum mechanics. You know the first postulate of quantum mechanics?
First postulate of quantum mechanics.
The first postulate.
That's reading my mind right now.
Okay. How about you? First postulate of quantum mechanics? Anybody? Oh. Okay, first postulate of quantum mechanics says the system is the wave function. Your wave function represents the system. Right? Now, the wave function, how do we get the wave function? By solving Schrödinger's equation. Right? So your energy is the expectation value of your wave function with the Hamiltonian operator. Right? So literally, your system is defined via its energy. So it's pretty much the most important property you can have. Right? Clearly stands out. All right. The energy is the expectation value. And we know an expectation value right? The expectation value in our ensemble, right? So it's the average of the energies of all the individual systems, right? Each system can have a different state, but you have capital A many systems, right? So expectation value of E in ensemble with A systems. Okay. We have the probability. So it's the probability weighted. Let me go with J again. Energy contribution of every state J. Okay. So this already represents the trick, right? We don't sum over systems anymore, over the A systems. Now we sum over the states, right? Now we can insert this, right? So now we have E minus beta EJ over Q. Now we pull the Q in front. It doesn't depend on the sum. If E minus beta EJ. Now, observe that if I differentiate with respect to beta, the sum E minus beta EJ, what do I get? My beta is in every summand. So I get a sum again, but I differentiate an exponential equation, I get an exponential again, right? You know this joke, two functions crossing each other, and then the one says to the other, move away or I'll differentiate you. And then the other function says, too bad for you, I'm an exponential function. We have E minus beta EJ, but you get also what's in the exponent minus EJ. Right? So if you look at this and this, looks pretty similar apart from the sign. So this means my expectation average is 1 over Q times derivative of the beta. And this sum here is Q, right? So I can write Q here. And then all I need is the sign, right? So I still get a sign change, minus 1 over Q. Derivative of Q with respect to beta. Now, then again, observe or recall if I want to derive the logarithm of f with respect to its variable, that's the same as 1 over f times exf. And so that's exactly what we have. So my expectation value is minus d beta logarithm of q. So this is also what you would consider your internal energy U and traditional thermodynamics notation. Right? Are there any questions on this? Is the derivation clear? Yes, please.
Please explain how you got the first expectation value again.
This year?
No.
So I inserted for P my Boltzmann probability here. Make sense?
Yeah.
Any other questions? We are at the end of today's lecture. I'd like to thank you for your attention, and I'll see you next week.